Okay, hi folks, thank you for joining us today, when we have the pleasure to have Ian Gemp to present his work in approximating Nash Equilibria in normal form games that was recently accepted at Clear 2024. For those of you who don't know Ian is a research scientist at Google DeepMind in London that's been working on game theory and multi-agent systems, and his main interest is in searching for instances of game in the wild, problem settings exhibiting a conflict of agents' incentives, as well as opportunities where game-theoretic techniques can be used to power broader AI models. In either of these cases, he believes that we need powerful game solvers, which have been his longest running research focus for a long time. And as a background, Ian received a bachelor in mechanical engineering and a master's in applied math from Northwestern University, and as well as a PhD a master and a PhD in computer science from the University of Massachusetts Amherst. So we're really grateful to have you today, Ian. And without any further ado, please, you can have the floor.
All right, thank you. Yeah, and thank you, Manfred and Rapali, for the invitation and the warm introduction. Yeah, so like Manfred said, this paper I'll present at iClear in May, and it's joint work with Luke Maris and Georgios Biliouras, who are both colleagues of mine here at Google DeepMind. Okay, so this research is all about solving normal form games, which, based on some of the feedback, which I guess will be made public in open review, or maybe it was, so this, yeah, sorry. I submitted this paper to NeurIPS. It was rejected there, and one of the critiques was that normal form games might not be relevant anymore, and like we really should be focusing on extensive form games. I want to make the argument that normal form games are kind of fundamental, and if you solve problems here, that'll help you solve the more complex game settings. But just to remind you what a normal form game is, something like rock, paper, scissors is an example. And so on the right, you'll see the payoff matrix for rock, paper, scissors. In every cell, the left entry is the payoff to the row player, and the right entry is the payoff to the column player. And we want to, given this matrix, we want to solve for a Nash equilibrium, which in rock, paper, scissors is a uniform strategy for both players. Okay, but like I just said, normal form games form the foundation or the root node of the tree of game theory challenges. If you solve normal form games, there's ways of taking those techniques and solving, for instance, extensive form games with some modifications. If you're familiar with sequence form, it looks just like normal form, except now a simplex becomes a triplex when you start looking at the math. You can also use normal form game oracles to solve non-stationary multi-agent RL problems. Normal form game solvers are critical to a step within PSRO that allows you to solve a wide range of games. And so in this work, I'm not going to focus on rock, paper, scissors. We're going to focus on n-player general sum games. So your typical payoff matrix will now, it won't sum to 0 if you look at every cell, but also we're going to have tensors instead of payoff matrices because we'll have more than 2 players. There's actually a paper at iClear that'll be presented this year on a black box approach for non-stationary multi-agent reinforcement learning that uses game solvers as oracles in a more complicated algorithm. But you can see when in their table here, as they start to list out all of the types of games and the rates of convergence for different algorithms for learning an equilibrium, they kind of skip over general sum Nash equilibrium. And so hopefully this work can kind of fill that gap that's there. Okay, so that's the motivation for looking at normal form games. In this work, we take a specific approach to solving normal form games that's more inspired by the success of machine learning. So machine learning, or at least a large proportion of it, that we see at like the AI conferences now relies on stochastic optimization techniques. So stochastic optimization has allowed us to solve very high dimensional optimization problems. A lot of these are non-convex. So for instance, neural network training. A lot of the times we use variants of gradient descent. These are super efficient, and somehow they're able to circumvent a lot of the issues that we usually would guess would occur with non-convex optimization. But one of the things you really need to get these to work is unbiased estimators. So like we typically train neural networks with mini batch training. If we had to use full batches, nothing would be possible in deep learning. So we really need unbiased estimators to make this possible. Typically in normal form game Nash equilibrium approximation, our goals are we desire low exploitability. So these are strategy profiles where no single player can unilaterally exploit that strategy profile. And so our goal here will be to take machine learning as inspiration and build an unbiased estimator of exploitability and then minimize it. So this is an approach that has not been tried before and we hope might be successful. Okay, so I'm going to go through a couple of the key mathematical ideas that allow you to construct an unbiased estimator, and then talk about two techniques that we use to minimize this estimator. One is SGD, which everybody I'm sure is familiar with, and the other is a family of bandit algorithms, but that have global guarantees to global minima. Okay. Also, feel free to shout, excuse me, shout at me, because I have to switch between tabs to know if people are asking questions. All right, so the first thing that we need to be aware of is like why this problem is hard. So I'm calling this the curses of multi-agent. I think the curse of multi-agent has already been coined, and that typically refers to high dimensionality. So as you increase the number of players, that makes the problem grow. But there's also a problem of biased estimators when talking about exploitability. Okay, so the first one, in a normal form game, you have a utility for player I that is associated with every possible joint action. And if I want to know the expected utility for that player, I'm going to sum over all of those possible pure joint actions, and then compute what is the probability of all the players playing that joint action together. And yeah, sum this up. But this requires a sum over every joint action to compute this utility exactly an expectation. And it scales as m, where m is the number of actions, to n, the number of players. So that's the curse of curse of multi-agent in terms of high dimensionality. As you increase the number of players, the number of joint actions that you have to marginalize over scales exponentially. Okay. And maybe I'll go a bit slower on this slide. So yeah, U is utility, I refers to player I in this subscript. X is a full strategy profile. So it's a mixed strategy for every player. A, this is our joint action space. We're taking a product over players J here. So X sub J is player J's component of the strategy profile. And then A sub J here refers to the specific action index. So what is the probability of player J playing action A sub J? Okay. Then the second problem, though, that I want to point out is that in order to compute what is typically like the value of interest in games, is this exploitability formula here. We have a bunch of max operators. So we ask the question, if everybody is at this current strategy profile X, and we keep all players other than player K fixed and allow player K to change their strategy unilaterally in order to maximize their utility, how much can they gain? So I'm going to call players, the amount player K can gain epsilon sub K. And then the exploitability is what's the maximum that any player can gain by exploiting X. And so this is 0 for a Nash equilibrium. But let's say let's say X is a mixed strategy here, and I want to try to estimate this without trying to go back and compute the exact expectations for these utilities. So what that means is it means this will be a random variable. We'll get an estimate of it, but it's a random variable. This will be a random variable as well. And so we're going to end up trying to compute a max over a random variable, which in general gives you an unbiased estimate. And so we'll see it's not just maxes. There's, anytime you have kind of a nonlinear operator, a nonlinear function of a random variable, this becomes a challenge. There are certain cases like polynomials where you can do tricks to still construct unbiased estimators. But in general, getting an unbiased estimator of something like exploitability is not as easy as it is in, let's say, deep learning, where I just grab a mini batch of data, compute my loss for each of those data points, and then average that. So we have to do something a bit more clever to get around this issue. Okay, there's a number of loss functions that people have already created for games for the purpose of you minimize the loss function. And if you find that you're at a global min of the loss function, then you're also at a Nash equilibrium of the game. And so there's a list here, but for reasons similar to the one that I just talked about with the max introducing bias into your estimate, none of these give you unbiased estimates. So none of them are really suitable to running something like stochastic gradient descent, which assumes you're going to get an unbiased estimate of a gradient. Okay, so those are the two kind of problems that make solving games hard, or at least there are many, but those are two. The next thing that we're going to exploit is the geometry of the simplex, and specifically its tangent space. So I'll go into what that means, but I just want to generate some intuition first. So let's say you're in a game and you're going to hold all players fixed except for player 1. And player 1 has 2 actions. So it has its probability of playing action 1, and it has its probability of playing action 2. And this is its simplex, and this is the line x11 plus x12 equals 1. So this is our probability simplex. And let's say player 1's current strategy is at this point on the simplex. And then let's say we compute player 1's gradient. This is the direction in which it wants to change its strategy in order to maximize its utility, and it points in this direction. All right, so intuitively, a Nash is a strategy profile which no player has any incentive to change their strategy. So in this case, could we be at a Nash equilibrium? I think for the sake of not like letting anybody answer this, all these questions are going to be on these slides. I'll just answer them myself. So no, we're not at a Nash equilibrium. You can just like see from the diagram, like if I move here and I project back onto the simplex, I'll be here. So like I had an incentive to move. I'm not back at the same point, so I'm not at a Nash. Okay, and that's what I've just drawn there. That's the projection. Okay, so now I'm going to ask the same question here. Here, am I at a Nash equilibrium? Well, like you can argue maybe I didn't draw this perfectly, but yeah, it's possible. I mean, I have to check this for every player, but at least this player doesn't look like they have an incentive to deviate because their gradient points this way, and then I project back down and I get back to the same point. So there was no reason for them to deviate. Okay, so that is a Nash. Now, what about this point? Okay, well, this point, I'm going to take a step here and then project back to the simplex, and I project back to the same point. So yeah, it is possible I'm at a Nash. But this case is a bit trickier because we're at a corner of the simplex. Okay, but I want to revisit the first example I gave. So we're at this point, and we did this, thought process where we move to this point and then we project back onto the simplex. But equivalently, I can think about, instead of performing like an update step of gradient ascent and then projecting, I can talk about projecting the gradient vector itself onto the tangent space of the simplex. So that just means essentially to reject the component of the gradient that is aligned with the 1, 1 vector. So that's the normal vector to the simplex. And the formula for projecting the gradient is just to subtract the mean. So it's a linear operation, but this matrix, all it does is when you apply it to a vector on the right here, is it just subtracts the mean of the vector. And so you can think about this as like starting to measure if the variance of the gradient vector is 0. But so what I want to point out is really we should be worrying about these green vectors, the vectors that live in the tangent space of the simplex, and asking if those are 0. If those have norm 0, then we know that we're at at least that player has no incentive to deviate. And this is true except when you're at corners. So if you're anywhere in the interior of the simplex, that's true. If you're at a corner, though, in this case, if we computed the vector in the tangent space, I should have drawn it, but it would be a vector like this, and this doesn't have norm 0, which would suggest to us, oh, maybe we're not at a Nash, but it is possible because the projection brings us back to this corner point. So the corner points are tricky, but I'll explain a way around those. But please stop me here if you have any questions. Okay. Okay, so now we're going to extend to partially mixed equilibria, meaning that we're going to handle these corners. So we're going to do that kind of by cheating. So we're going to add an entropy bonus to each player's payoff. So if we do this, we can ensure that every player's strategy lies in the interior. So we never have to deal with corners. So it's known that if you add entropy bonuses to player utilities like this, so I'm going to take my original utility and then I'm going to add on tau times the entropy of their strategy, that when you compute the Nash of this transform game, you get QREs. And QREs always have fully mixed strategies. So now we're never at a corner, so we don't have to deal with that case. But now our gradients become the original gradient that we were seeing before, minus tau times log of xk plus 1. And so now we'll just we'll go through the same procedure as before. We'll compute our gradient. It'll be the gradient minus tau, and then we'll measure, is the projected gradient in the tangent space 0 norm, and if it is, it means we don't have any incentive to deviate. Yeah, go ahead.
Yeah, it was just a clarification. When you're saying QRE is a quantum response equilibrium?
Yeah, sorry. Yeah, quantum response equilibrium, specifically logic equilibrium. Yep. Go ahead, Pranay.
Does this give us a sense of the boundedness of the rationality of the agents?
So QREs have been used for that. So like if you play around with that temperature tau, that can be used to control the boundedness of agents. I don't know exactly how boundedness is defined in terms of tau, but I know that's a motivation for QREs.
Yeah, if it goes to infinity, it's unbounded. The closer it goes to 0, maximizes by utility. And it goes to minus infinity, I think, is anti-rational. So,
okay.
Yeah, I think that's a relationship.
We'll make I guess one thing to say is that we're making this change, but we're going to show that a relationship back to the original problem we want to solve, which is for Nash equilibria, not QREs. And I'll explain that relationship later, or at least I'll point out what it is. But we're doing this temporarily so that we can build a loss that only checks to see is the projected gradient in the tangent space, does it have 0 norm? If it does for all players, then we know we're at a QRE, and then yeah, I'll explain that at low temperature QREs are basically approximate Nash equilibria. Okay. All right, so those are kind of the key mathematical ideas, and now we're gonna build a loss function that we can obtain an unbiased estimator for. So the loss function is pretty simple. It's what I just described. So this is the gradient. So it's the player's gradient, then minus tau times that log of xk plus 1. Then you project it, which means you just take that vector and subtract off its mean. And now you take the squared norm of it. Eta k here is just a scalar. You can, as long as it's positive, that's fine. And now if we sum this up, this is a suitable loss function, because we know if we minimize this to 0, which is the lowest possible value it could have, because this is a positive quantity, that it must mean that all of these projected gradients are 0 and we're at a Nash. No player has any incentive to deviate. We can also prove that we can use this loss to construct an upper bound on the true exploitability in the original game. So there's a term here, this first term here depends on the temperature. So for lower and lower temperature, this term becomes smaller and smaller. And then for, in this term, for lower and lower loss, you take the square root of it, and then it has this coefficient in front, but the exploitability becomes smaller as well. So you can go ahead, minimize this loss function, measure what the loss is, and it'll give you an upper bound on what the exploitability is for that strategy profile. So by solving for QREs at low temperature using this optimization approach, you can still recover approximate Nash equilibria. Okay, and then another thing that we need to explain is how to construct an unbiased estimator of this loss. So this is spelling out the loss just like in longer form. So each of these is the projected gradient. So you can see I have these player K's gradient here. Sorry, these should have taus next to them. But these are player K's gradients. This operation is just subtracting off the mean of the gradient. And the same thing here. The 1 and 2 refer to the fact that these need to be 2 different unbiased estimators. So you need to compute, you need to get 1 unbiased estimate of a gradient. And the way to do that is easy. You just ask, for instance, let's say we're playing rock, paper, scissors. I ask the other player to sample 1 pure action from their strategy. So that, let's say they play rock. And then I evaluate rock, paper, and scissors against each one of their, against rock, and that forms my gradient vector. And then I subtract this off, and that gives me an unbiased estimate of this projected gradient. Now I just repeat that procedure, and that gives me a second one. And now I take the inner product, and then I sum this up. I do this for all players, and that gives me an unbiased estimate of this loss. Now, the reason I need to do 2 separate estimates is because the expected value of, let's say, x squared is not equal to the expected value of x quantity squared. But if I use 2 independent estimates by linearity of expectation, or by independence, I can pull these terms, or I can bring an expectation in here and have a separate expectation here, and then everything is fine. Right. And then, sorry, go ahead.
Hi, Ian.
Yep.
So the expectation is the outer expectation, because this smells a little bit like a nested expectation, because you have the expectation and then the sum. The outer expectation is with respect to what?
You're asking, like, what is the subscript here?
Yes.
So yeah, sorry. In the appendix of the paper, I'm a bit more rigorous, but you can say it's just like a joint distribution over gradient 1 and gradient 2. So this gradient 1 and gradient 2 are identically distributed.
Right.
And
Yeah.
so just say it's like saying x taken from p of x and y taken from p of y, where p of x equals p of y.
Right. Yeah, just to make sure that this is not like a nested expectation, because otherwise this wouldn't be as easy to compute. Now, because you have expectation and then you have another summation on k. So that means for every k, for every p of x, then you have a summation of k. So this is linear. This is what you said. This would
Everything's linear. Yeah.
Oh, it would be ON in computational time.
So the cost of getting a single unbiased estimate of this loss is 2nm. So I have a sum over n players. In order to get an unbiased estimate of a gradient, I need m calculations, because I need to compare rock to rock, paper to rock, and scissors to rock if rock was sampled from the other player's strategy. And then I need 2 because I need 2 separate estimates. So we have a table in the paper, and this is not the only way to construct an unbiased estimate. There's lots of ways, but what makes this possible is that projecting the gradient is a linear operation, and that expectations of products is doable by this trick where you use an independent sample for each entry.
Yes, thank you.
Thanks. So this block is just what I described to get before. To get an unbiased estimate of this gradient, you sample a single action from every other player's current strategy. So this works in n player as well. And then you evaluate every one of your actions against that background joint action. And then you return the vector of payoffs as this gradient. And then I just wanted to make sure that it was clear that you can use the same estimate here and here. And then here and here are the same as well. Okay, so now I want to give some intuition for what this loss landscape looks like for familiar games. So in the top row is the chicken game. On the vertical axis here is player 1's probability of swerving as opposed to going straight. And on the horizontal axis is player 2's probability of swerving. This top row is showing Nash conv, if you're familiar with that. So that's just the sum of the epsilon sub k's. So that's how much can each player gain by deviating unilaterally, and then we add that up. And then each column over, so this is 0 temperature, and each column over increases the temperature a little bit, just to show what this loss landscape looks like. So this is Nash conv, so this is not our loss. This is the top row. And the chicken game has 3 equilibria. There's one at a corner here. That's a pure equilibrium. There's another one here. And then there should be a mixed strategy here. But what I'm showing is that Nash conv, because of this max operator that's hidden in the epsilon sub k term, is biased. And so it actually, if you plot the landscape, you don't see any local minimum here at all. So it has no idea that there's a mixed Nash equilibrium. Whereas if you take the loss that we're proposing and you look at 0 temperature, remember, without the temperature, we can't capture corners of the simplex correctly at all. So in this case, the only Nash equilibrium we see is the fully mixed one here. If you increase the temperature, though, even a little bit, you start to see, and sorry it's so small, a little bit of a minimum here and a little bit here. And if I increase it a little bit further, it becomes more clear that there's these local minima near the boundaries. And I think I have a plot later that shows this in logit space, so it's easier to see. But the point is that this loss landscape actually captures all equilibria and is an unbiased estimate. Okay. So now that we've created this loss function, and I guess one thing I should point out is this loss function is necessarily non-convex for a lot of problems, and that's because it's trying to capture the fact that this loss should be 0 at a Nash equilibrium. So if you have more than more than one distinct Nash equilibrium, it has to be non-convex because it has to hit 0 somewhere and then increase in between. But we then thought, okay, let's see what researchers did to analyze non-convex landscapes for neural networks. Maybe things aren't as bad as we would think. So what we did is we looked at in this case 5 different games. These are extensive form games. I'm not going to go into detail exactly about how we constructed normal form games from these, but basically we took like slices of the games that were normal forms, where we considered a restricted set of actions available to each player. I think we considered 6 actions per player. And then after getting these normal form games, we then redid an analysis that was done by, in this paper, identifying and attacking the saddle point problem in high-dimensional non-convex optimization in 2014. And so in each of these plots, let's look at 2-player sheriff first. On the x-axis, you can see the norm of the projected gradient of our loss. And then on the y-axis, you can see the exploitability. And then in the color, what the color indicates is the index of a critical point. So what that means is if you're in dark blue here, it means the loss surface locally looks convex. So it looks like it has positive curvature. If you're the index of your critical point is higher, so what it's measuring is the fraction of eigenvalues in the Hessian that are negative. So if your critical point, your index is 0.3, it means that 30% of the eigenvalues of the Hessian are negative, which means you have a saddle point. And so in this case, you can see that the higher the norm of the projected gradient is, so like the higher our the higher the exploitability is, so like the higher our loss is, the more likely we're going to be at a saddle point as we move further down to where the norm of the projected gradient of our loss is near 0. We find that we're actually near local minima. So it means that as you search the loss landscape and you search it at like lower and lower value level sets, you're going to find minima, not saddle points, not maxima. So this is kind of replicating a similar phenomena that we see in neural networks that suggests that it shouldn't be that hard to optimize to find Nash equilibria in these games. Okay, so then the first technique that we're going to try out is just SGD and use that to try to solve for Nash. I told you we can construct unbiased estimates. I haven't included a slide here on what the gradient of this loss is, but it's available in the paper on arXiv, and we have the formula for it. We actually have the formula for the Hessian as well. We didn't run Newton's method, but you could. But here's the performance if you run SGD. On the y-axis here, we're measuring NashConv, or like something like NashConv. On the x-axis is the iterations of the algorithms. This is a modified Shapley's game, which is a 2-player, I believe, maybe 3-action game. I'm forgetting. Oh, I say here. Yeah, 2-player, 3-action game. The yellow curves are regret matching. The green curves are follow the regularized leader. The red curves are from a previous paper we worked on, and it uses kind of a homotopy approach, meaning it tries to solve for QREs as temperature is annealed over training. And then in blue are our new approach, And in the legend here, S refers to the number of samples we use to, essentially like mini batch samples we use to estimate the gradient. And as you can see here, S equals 2, and that's because we need, remember, 2 independent estimates of each gradient. So that's like the minimum number of gradient estimates we can do to get an unbiased estimate is 2. Is there a question? No.
There was
yeah.
there was a previous question from Alexander. I can read it for you. He was asking, what's the intuition behind necessity of using the tangent space for the projection in the loss function? He's asking if it is because we optimize on the simple on the simplex and in a simple thing to project onto.
Yes. Here, let me scroll back out. Yeah. It is because we're on the simplex. So this is projecting a gradient onto the tangent space of the simplex is a simple operation. You just take this matrix and you left multiply it by the gradient here, and all this does is subtract off the mean of the gradient. And yeah, this is something we can only do on the simplex, or I should say like on a hyperplane. So because players' strategies obey linear equality constraints, that being this one here, we can perform this operation. So there's a way of doing this for any system that satisfies linear equality constraints, but that's beyond the scope of this. Hopefully that answers. Okay. So we can see that SGD does really well in this problem. We can actually show that for Shapley's, the loss landscape that's induced by this game is strongly convex. So then it makes sense that SGD would work so well. Gamut is a benchmark library for solving games. And we chose this game, the D7 covariant game, because in a paper that we cite, this was the hardest game, so we wanted to see how it performed. And these are also games where regret matching and follow the regularized leader don't necessarily work. So this Gamut D7 covariant game is 6-player 5-action. And these no regret algorithms are not guaranteed to converge to Nash equilibria beyond 2-player 0-sum. So that's what we're showing. Regret matching actually diverges here. FTRL, I think, is trying to make slow progress, but this SGD approach does quite well. And then these are 2 Blotto games, and the maroon lines you can see actually do reach down to low exploitability, so these perform the best. The blue lines seem to be approaching an asymptote, and we actually, because we have a formula for the Hessian, we can look at the eigenvalues of the Hessian here, and we can show that there's positive and negative ones. So this looks like SGD is getting slowed at saddle points in both these cases. And so there are techniques for avoiding saddle points that people in deep learning have developed. We didn't try these out here, but we're hoping that transforming the Nash equilibrium problem into a non-convex optimization problem might allow us to try out some of these new techniques and see if it can't be competitive with other approaches. Okay, and I just want to remind people, like, to have this loss landscape in your head about what some of the challenges might be. So I already showed you this chicken game before. Here's Prisoner's Dilemma, which has a unique pure Nash of defect effect. So at temperature tau equals 0 in this pane here, you can see it's like an even uniform color across the landscape. So our loss does not see any Nash equilibrium at all because they're all pure, and it only sees mixed Nash equilibria. But if we increase the temperature a bit, you can see that this minimum starts to appear in the corner. And so when you're optimizing over this landscape, you need to worry about like, is my temperature low enough? Or sorry, is my temperature high enough? It needs to be above 0, but it might be hard for it to, like if it starts over here, to find this minimum all the way over here if the landscape in between is really flat and then gets steep near the solution. Similarly, this landscape is non-convex. I wish I had an example of a landscape that I could plot in 2D, like a game whose landscape, when I plotted in 2D, showed local minima. These appear to all be global minima that are Nash equilibria. So it kind of makes it look like the problem is too easy. But yeah, we need to use our same intuition that we use for deep learning to understand how to get solvers to work in these regimes. And these are the same plots, but in logit space, which make it clearer the distinction between equilibria. So you can see like there's space in between these three. So these represent the two pure, and this is the one mixed in the middle. And then if we increase the temperature too high, they kind of start to blend together. And if the temperature goes to infinity, the solution becomes the uniform strategy. Okay. So the last thing I want to talk about, because we know SGD does not give you global convergence guarantees to global minima, there are methods that people in machine learning have worked on that give you global guarantees. They're not gradient-based methods. They take a very different approach. Yep, question?
Yeah, before that, there's a question in the chat by Alexander. And they ask, do we need at least two unbiased estimators? Would increasing the number of estimators give us something in terms of convergence guarantees?
We need two unbiased so they can be the same same estimator. You just need to run it twice. So you need to get two independent samples. So that's this grad superscript 1 here and grad superscript 2. So you do need these two. Increasing the number of samples will make this, will reduce the variance of this loss function and reduce the variance of your gradient estimates, which can accelerate convergence. And I'll actually, yeah, I'll mention that in the conclusion, but just increasing the number of samples is only one way to reduce the variance. There are other techniques that, again, have been developed by folks in stochastic optimization to reduce variance of gradient estimates. But yeah, that's a good point.
But it's always two variables that you need in there, right? Here you have K1 and K2, for example.
So this is at least the most common way I know of producing an unbiased estimate when you have like an expectation of a product here. It's not the only way. There are, for instance, I think it's called like the Russian roulette estimator. And this estimator is like more powerful in a sense, but can have like infinite variance in some cases. It's an estimator where you keep flipping a coin, asking if like, okay, should I ask for one more sample? And it doesn't have a deterministic endpoint of when to stop asking for samples. That's just one other example. But I don't want to make a general statement that you always have to have two estimators, but this is at least the most common approach I know. Okay, so for this last family of techniques called Xarm bandits, and again, this is not the only global optimization technique, but it's one that we wanted to try out. In this case, you build a mesh over your feasible set. So let's say you're just trying to optimize a function over the real line here, or like a line segment between 0 and 1. You start by splitting your space in half. So like anything less than 0.5 and anything greater than 0.5. And then you build a tree where you just progressively split each cell in half. Oops, sorry. And as you build this mesh, you can think of like every node here can be an arm pool. So this is how it becomes a bandit algorithm. And every time you evaluate a point, that's where you evaluate your loss function. So it builds a mesh over the entire feasible set, and it starts pulling arms everywhere. And if it finds out that certain regions are returning like low values, then it refines its mesh in that region. It's kind of a cool approach. And so that's the technique we tried out. In practice, these algorithms don't scale very well to high dimensions, but they do give you theoretical results. And one of our goals was to try to land a convergence guarantee in n-player general sum, which has been elusive so far. So we have to make one assumption in order to apply the convergence guarantees from that Xarm bandits to our setting. And what it amounts to in the global optimization setting is you ask that every global minimum have a positive definite Hessian. So every global minimum essentially needs to look convex, and that strongly convex. So it needs to look like an x squared function, but can't look like an x to the fourth function, which is not strongly convex. I'm kind of oversimplifying that assumption because x to the fourth is actually also fine, but it's essentially like that, and that translates into like game theory parlance by saying we need every Nash equilibrium to be polymatrix isolated. And what that means is that if you were to give me a strategy profile X and then ask me and say it was a Nash equilibrium, and then you asked me to build a polymatrix approximation to the game, a local polymatrix approximation, which you do by just you grab every opponent in the game, and you both figure out what the payoff is between every pair of your joint actions, given that everybody else samples from their strategy, and that gives you one of the bimatrix games between a pair of players. You build out all of these. That's a polymatrix game. You give the polymatrix game to a solver, and you say, okay, is this Nash equilibrium isolated, meaning that there are no other Nash equilibrium locally nearby? And if that's the case, then it's locally polymatrix isolated. Sorry, that was a bit wordy, but again, we make this assumption, and I'm not going to go through this. That doesn't matter. But if all the equilibria are polymatrix isolated, then bandits can approximate one of the equilibria with high probability in t to the -1/4 iterations. So this is not something that I would say is like a practically useful approach, but it does tell us that under mild assumptions, equilibria can be approximated in polynomial time. So it's a nice positive result because there are a lot of negative results in computing equilibria. And this plot is just to give you a visual of what that looks like for solving for an equilibria in a game. So on the y-axis here is the exploitability. The black line is like the true exploitability. So this is the epsilon we actually care about. And you can see that there's 1, 2, 3, 4, 5 Nash equilibria. Our upper bound in red that doesn't include any entropy bonus captures all of these interior equilibria, but doesn't capture the one at the boundary. If we increase the temperature to 0.01, we shift the solutions a bit. So now we're not perfectly on Nash equilibria, but we do capture this pure equilibrium. So we do recognize that there is a pure Nash equilibrium. And in this case, we're playing a 7-player symmetric 2-action game. Symmetric, and we're going to look for a symmetric Nash. So symmetric means that we're going to assume everybody has the same mixed strategy at a Nash equilibrium. So we only need to look for one of those players' mixed strategy. And then 2-action means we can represent every 2-action mixed strategy by just a single probability. And so that's why on the x-axis here, there's only one. We only have a univariate search space. So this is the probability of selecting action 1 of 2. And this bandit algorithm tries pulling a bunch of these arms. So it tries evaluating all of these probabilities. And in what I've circled here are the best solutions it's found over the course of its search. And it finally settles on this one. And then these numbers in the boxes are the welfare of each of these equilibria. Ideally, it would be nice if we could have found this max welfare equilibrium, but that's kind of future work. So I see I only have 4 minutes, so I'm going to conclude. The takeaways here are that we provide an efficient and unbiased upper bound on the exploitability epsilon, and that allows us to construct a loss. And we use that to show that Nash equilibria are provably approximately correct solvable at a t to the minus 1/4 rate under mild assumptions. That's that polymatrix assumption. And then SGD works fairly well despite non-convexity. So it had some troubles, but same troubles that we had training neural networks. So maybe we can circumvent these. In follow-up research, we'd like to extend some of this work to extensive form games, pseudo games, Markov games, things like that. Somebody mentioned, well, yeah, we talked a lot about the unbiased estimation and what to do with estimators. It'd be nice to reduce the variance and use like control variates or something. Try out different bandit algorithms and other globally convergent algorithms like Gaussian processes, and try out better gradient optimizers like Atom and things like that. But I'll stop there. Thank you very much for having me to the seminar, and I'm happy to take any more questions that there are.
Awesome. Thank you, Ian. I think we have some questions in the chat that in the interest of time, we defer to the end. Let me try to parse them from the chat. So Alexander, I think I had another question. It says, do we need at least 2 unbiased estimators? For example, increasing the number of estimators give us something in terms of convergence guarantee or convergence rate. So if I understand correctly, yeah.
I think I might have inadvertently answered that one earlier. I might have been answering the question earlier, but yeah. Okay.
And the second question is, if this, I don't know what this was referring to, Alexander, if you can clarify that. I think he doesn't have audio, but he's saying that if your approach of loss function works fine, so by work fine, I think he says it's probably approximately correct with Xarm bandits, assuming the game is polymatrix.
Sorry, no, the game can be n-player general sum, not polymatrix, just normal form. But the assumption we make is that if you can, for any like mixed strategy profile, you can build a local polymatrix game around that strategy profile using the normal form game. And it's a matter of like marginalizing the full normal form game tensor along certain dimensions. So yeah, there's like a local polymatrix approximation that you can build, and then you ask, it's the same, it's like the analogy of asking like, okay, I want to build a quadratic function locally around a point, or do a Taylor series expansion around a point for a loss function. For a game, you build like a polymatrix approximation, and that's like a second order approximation to the game.
Okay, William.
Sorry,
thank you.
Before that, yeah, since we're at the hour, if we could just like thank the speaker, and we can stop the recording, I think. And lastly, Ian, do you have like some extra time since we're at the